Visual communication is fundamental to sharing information. For example, we use weather maps to interpret weather patterns, fMRI maps to interpret brain activity, and maps of pollution to understand human impact on the environment. Understanding how people infer meaning from visual features like color helps design visualizations that are easier to interpret. Several factors influence expectations about color meaning in color map visualizations. First is the dark is more bias, which leads to the expectation that darker colors should mean larger quantities. Another factor is the opaque is more bias, which leads to the inference that colors appearing more opaque map to larger quantities only when color maps appear to vary in opacity. On white backgrounds, darker colors appear more opaque, so the opaque is more bias and dark is more bias work together and lead to the expectation that darker colors should mean more. On black backgrounds, the two biases conflict because lighter colors appear more opaque, so people are more likely to infer that lighter colors mean more. The hotspot is more bias leads to the inference that regions appearing as hotspots map to more. When a hotspot is light, people expect lighter colors to mean larger quantities, but only when the hotspot is very salient. Finally, direct associations lead to the expectation that colors strongly associated with the domain concept represented in the visualization map to larger quantities of that concept. This has the potential to conflict with the dark is more bias when the domain concept, for example sunshine, is associated with light colors. From previous work, we expect that people should expect darker colors to mean more as long as color maps don't appear to vary in opacity, don't have a salient light hotspot, and don't represent a domain associated with light colors. We propose that there may be cases in which the conditions I discussed are met, yet people still infer lighter colors to mean more. For example, this color scale used in this color map has no appearance of opacity variation, no hotspots, and there can't be direct associations because the data don't represent a specific domain concept. However, there is a large dark area that matches the background. This could lead to the percept that the dark area looks empty or like a hole. This is illustrated below. Only the dark region should appear as a hole, while the light region should appear as filled in. Contrast this color map with the one on the right, which doesn't appear to have a hole. Although it has a large dark area, that area doesn't match the background, so it can't appear empty. We hypothesize that if a color map appears to have a hole, observers may infer that the hole maps to non-existence and therefore filled-in regions should map to more. If filled-in regions are light, then observers should infer that the light regions mean more. To test our hypothesis, we used the following design. Here's the color map I just presented, and we compared it with a color map that was unshifted, so the appearance of the hole goes away. We put these maps on a white background as well, so neither unshifted or shifted conditions should look like they have a hole. We referred to this as the continuous condition because these color maps appear relatively smooth. We additionally tested color maps that appeared coarse, which may have reduced the appearance of a hole. We repeated this experimental design for 10 color scales, some of which would be more likely to have holes depending on the endpoints of the color scales. Each participant saw one condition, and here are examples of two conditions with all stimuli. On each trial, participants were asked to indicate with left and right arrow keys where the measured numbers were larger. One side of each color map was dark, and one was light. This was counterbalanced across trials. To begin analyzing our results, we used hierarchical clustering to group color scales according to the probability that participants inferred the darker side represented more. We found that they fell into three families, which we labeled as follows. Monochromatic, which was the two monochromatic scales, although autumn was clustered here as well. The black and white endpoints family had black and white endpoints, although winter ended up here too. And spiral color scales spiraled through color space. The following slide will show responses averaged over these color scales in each cluster. If you'd like to see the data according to each color scale, please see supplemental material. This is the monochromatic condition. On the x-axis are the two data distribution conditions, shifted and unshifted. On the y-axis is the proportion of times participants responded that dark meant more, and chance is at 0.5. For the monochromatic coarse color maps, participants consistently inferred dark meant more across conditions. This pattern is expected because the color maps don't strongly appear to vary in opacity and don't appear to have holes. We found the same thing for the continuous maps. Next, we'll look at the conditions that test the hole hypothesis. As you can see, this was not supported. The hypothesis predicts dark more responses for all white background maps. For black background maps, it predicted dark more responses for unshifted maps and light more responses when maps were shifted. This is because the shifted maps would have appeared to have holes. This is not what we saw. For coarse maps, we saw consistent dark more responses, even for maps with the appearance of a hole. This is evidence against the hole hypothesis. For continuous maps, we saw dark more responses for unshifted maps and reduced dark more responses for both shifted conditions, even the one without the appearance of a hole. This is also evidence against the hole hypothesis. Finally, the hole hypothesis predicted results for spiral color scales to be similar to the monochromatic ones, with consistent dark more responses across conditions. This is clearly not the case. Although people generally inferred dark meant more, we also saw light more responses for the shifted continuous maps on the black background. This map should not have appeared to have a hole, so this result is particularly surprising. We started off with a question: do cases exist where people infer light means more when previous work suggests they should not? The hole hypothesis predicts that due to the presence of a hole, people should infer light means more on this color map. However, this is not what we found. Responses were at chance. In contrast, people inferred light is more on color maps where they should not have, like the one on the right. Ultimately, we aim to build a comprehensive model predicting people's expectations about color meanings and visualizations. We can use this model to create a tool that recommends effective colors for color map visualizations. However, doing so will require addressing open questions to build a deeper understanding of color meaning for visual communication.